this is the plan today. First, I'm going to give the motivation for the whole project, as well as introduce you to the Archimedean lattices. And then I'm going to show you the bench structures of a few chosen lattices that I calculated using the type-binding method, including S and P orbitals. And then I'm going to show you the topological edge states that I found in some of these systems, and the quantum spin Hall conductivity that I calculated. And to start with, we need a little bit of motivation. With the development of social media platforms, as well as technology on mobile devices, allowing us to take photos and videos in high resolution, and the explosion in researching and commercial usage of artificial intelligence, we are creating data huge in size at the pace like never before. And here I took a diagram from the Forbes magazine showing the growth in the total amount of data that the world creates over the year. And they anticipated by the end of 2025, we will create a total of 175 zettabytes. And 1 zettabyte is equal to 10 to the power of 21 gigabytes, which is really huge. And this means that we are putting a lot of pressure and demand on storage facilities. And this poses a new challenge for us, material scientists, to come up with new storage technology with higher efficiency. And one important aspect of storage devices is how to read and write information, or in other words, how to interact with or how to manipulate spin states. And for that purpose, we need to be able to generate stable spin current. And one possible mechanism that we can look to execute this task is the quantum spin Hall effect. This effect exists in two-dimensional system, and while the total charge current is 0, you have flowing spin current on the edge of the system in 2 stable spin current channels, one for spin up and one for spin down. And this effect was theoretically predicted by Ken and Manley back in 2005 for time reversal symmetric systems. And they did this by proposing a very simple type-binding model and solve it for the ribbon geometry of graphene. And here I directly took the result from the paper. This is the bench structure that they calculated using the model. And you can clearly see the edge states for the spin current. And what is so special about these edge states? Well, the answer is that they are topologically protected, so they are very stable against disorder. And this brings me to the next point in my talk, which is topology in condensed matter physics. But first, we need to talk a little bit about topology in mathematics. So topology is a subfield in mathematics that study how to classify objects under smooth transformations. And this transformation could be stretching, twisting, bending, but poking a hole or closing a hole is not allowed, which means under smooth transformation, the number of holes of an object, the genus, stay constant. So it is a topological invariant of the object. And one famous example that I think a lot of people here know is the sphere and the donut. So the sphere has no holes, so G is equal to 0, and the donut has 1 hole, so G is equal to 1. And the next question that we should ask is how to calculate the genus of an arbitrary object. And the answer is given by the Gauss-Bonnet theorem. And here you calculate the Euler characteristic chi by integrating the Gaussian curvature over the surface of the object, and then relate it to the genus by 2 minus 2g. And in the case of the sphere, where the Gaussian curvature is 1 over the square of the radius, you can quickly check that g is equal to 0. And then now we have to take the next step and ask ourselves, how do we apply all these ideas to the band theory to classify matter? Or to be more specific, in our case, how to classify insulators. And so for that purpose, we need to find analogies between two fields, topology in physics and topology in mathematics. And because we're dealing with insulators, the band structure will have a band gap. So smooth transformation or deformation will correspond to processes that do not close the band gap, because the band gap can be considered as whole. The Bion zone in the momentum space has periodic boundary condition. So one edge is glued to the opposing edge, and it sort of defines a torus in the momentum space. And lastly, the topological invariant of the object, the Euler characteristic, has the analogy as the Chern number. So here is the Chern number of a certain band number n, and the Berry curvature, this quantity over here, gamma n, now takes on the role of the Gaussian curvature. And instead of integrating over the whole surface of the object, you integrate over the whole Biot zone, and when you divide the integral by 2 pi, you will also obtain an integer. And as a consequence of classifying matter with respect to their topological properties, we realize the existence of gapless edge states. And this can be explained by a hand-waving argument as follows. You consider the following setup: a normal insulator where the Chern number is equal to 0, and the topological insulator where the Chern number is not equal to 0. And they share a boundary and expand infinitely to opposite direction. And you start somewhere here, deep inside the region of the topological insulator, and slowly move towards the interface across to the other side, and you consider the band structure as a function to the interface. So somewhere along the way, the band structure has to close and reopen again, because otherwise you would have found a way to transform two band structures of these two materials into each other without closing the band gap, which is a contradiction because that would mean that they are topologically equivalent. So the band structure for this configuration should have a state bound to this interface and bridging the band gap. But the topological insulator of this type requires the time reversal symmetry to be broken. So now I want to talk a little bit about the time reversal symmetry. The time reversal symmetry operator, when acts on the wave function, turns the sign of the time argument, but it also changed the wave function into its conjugate complex counterpart. And by using this information, you can prove that the momentum operator under the effect of the t operator will flip the sign. And you can also show that the spin operator also flips the sign under the effect of the t operator. So altogether, you can conclude that the atomic spin-orbit coupling operator given by the scalar product of the orbital angular momentum L with the spin operator is invariant under the time reversal symmetry operator. Or in other words, this interaction respects the time reversal symmetry, and it allows a new kind of topological insulators, or the so-called Z2 insulators, or the quantum spin Hall insulator. And now if you consider a setup similar to before, where you have a topological insulator of this type sharing a boundary with a normal insulator, you will realize that there are two edge states bound to this interface, one for spin up and one for spin down, bridging the gap. And the existence of these edge states is always in pairs, and it is guaranteed by the Cramer theorem. This theorem states that for time reversal symmetric system with half integer spin, every eigenstate is twice degenerate. So in the gap, you only have the edge states because they are the only states that can bridge the band gap. So the energy inside the gap can only exist on these edge states. So that's why they always comes in pair. And here you can define the topological invariant nu as the number of pairs modulo 2. So if the number of pairs is even, you will have a normal insulator. But if the number of pairs is odd, you will have the topological insulator of this type. And now I want to introduce the system of my research in the master thesis, which is two-dimensional tiling. So tiling, or tessellation, is the covering of surface using different geometrical shapes with no gap or overlap between the shapes. And in the two-dimensional case, a tiling is called regular if all of the three following conditions are fulfilled. The first condition that all shapes are polygons and they are all regular, which means that the size of the polygons are equal. And the second condition is that the vertices are congruent, which means that the configuration of polygons for all vertices is the same. And the last condition for this tiling to be called regular is that you are only allowed to use one type of polygon. And there are in total 3 tiling of this type: the triangular, the square, and the honeycomb of the hexagon tiling. Now, if you leave out the last condition, which means you are allowed to use more than one type of polygon, you end up with the semi-regular tiling or the Archimedean tiling. And in the 2-dimensional plane, there are in total 8 tiling of this kind. The number here underneath tells you the configuration of the polygon on every vertices. And the number also tells you the number of sides that the polygon has. So for example, this rhombi trihexagonal tiling, 3, 4, 6, 4, means that you will find 1 triangle, 1 square, 1 hexagon, and 1 square on every vertices. And the most famous member of this family is the Kagome lattice that has already appeared in numerous works. And indeed, Topological Insider was predicted on the Kagome lattice back in 2009. And there are also works on the Archimedean lattices. So here, for example, this is a paper published by the group from Brazil. And there's also a work by the group of Professor Thomas Heine from Dresden. And this paper, not only do they study the Archimedean lattices, but also the demi-regular tiling. But all of this work has one thing in common. They use a very simple type-bending model with only 2 orbitals per side, one for spin up and one for spin down. And they use a very simple spin-orbit coupling operator that commute with SC, which does not reflect the entire properties of the spin-orbit coupling. Because if you look at the spin-orbit coupling, the atomic one, in this form, you will realize that it does not commute with SC. And the last point that I want to make is that the snap square lattice was used as a proximant for oxide quasicrystal. And here are 2 figures that I took from a paper from the group of Professor Vitra from our institute, which is the group that works on quasicrystal. And for all of this reason, we are motivated to study the topological properties of Archimedean lattices using the type-bending method, including S and P orbitals. And before jumping into the result, I want to briefly review the theoretical framework that we use in this thesis, which is the type-bending method. So the type-bending wave function ansatz is basically a linear combination of atomic orbitals. So phi sigma are the atomic orbitals localized on different lattice sites. Sigma is the index of the orbital in the basis. Ri is the Bravais lattice vector, and TL are the position of the atom inside the unit cell. And each atomic orbital goes into the linear combination with a different weight, C, which is dependent on the wave vector K. And here at the front, you have the phase vector to make sure that this and that is the block wave function, because we are dealing with crystal with perfect discrete translational symmetry, so the wave function has to satisfy the block theory. And now if you assume orthogonality between orbitals on different lattice sites and plug this ansatz into the Schrödinger equation, you will end up with a matrix eigenvalue problem where you solve for the eigenenergies E and K, as well as the weight C and K. And if you do it for every K point within the Bion zone, you will have the band structure of the material that you want to study. And in this project, we incorporate S and P orbitals into our calculation, so we are allowed to use this spin-orbit coupling operator. And for all the calculation, I wrote my own code using mainly 2 Python packages. The first package is ASE, Atomic Simulation Environment, to generate the lattices. And from that, I can get the information on orbital position, lattice vectors, the neighboring site of a given site, and also automatically generate a path to high symmetry points in the Bion zone. And I can feed all of these information to a second Python package called PyTB to set up the Hamiltonian for the type-bending model and solve the matrix eigenvalue problem over here. And as a result, of course, I will get the eigenenergies and therefore the band structures. I can get the eigenvectors, and I can even generate the Hamiltonian for each K point, which is important later on when I want to calculate the Berry curvature. And in this project, we took a fairly naive approach by assuming carbon atom on every lattice site, because graphene is a well-known perfectly flat system. And so for that, we can take the slated constant parameter of graphene for our type binding calculation. And the key feature of graphene is that the pz orbital is perpendicular to the two-dimensional plane, and it is decoupled from other orbitals inside the plane, and it is responsible for the free-moving electron on graphene. So for that reason, in many work, people just consider a simple type binding model including one or two orbital per side representing the pz orbital. So when you do a full calculation including s and p orbitals and then perform the projection on the pz orbitals, you should see a perfect mirror image similar to the calculation, to the simple type binding calculation. And here I demonstrated this for the case of the Kagome lattice. On the right hand side, you can see the famous band structure of the Kagome lattice with the fully flat band over the whole muon zone. And here is the full calculation with s and p orbitals. And I also performed the projection on the pz orbitals, which are highlighted in red. And you can see these two blocks of bands are similar to each other. And one of the reasons why the Kagome lattice is one of the favorite systems of the physicists over the last few years is because of these flat band. But if you take the next nearest neighbor hopping into the calculation, then the flat band will gain dispersion. And you can also see that the next nearest neighbor hopping also changed the total bandwidth of the band structure. And now we include spin-orbit coupling into our calculation. And for that purpose, you need to calculate the non-zero matrix element of this interaction within the type binding model. And first, you will need to write the p orbitals in terms of spherical harmonics, and then you can calculate the non-zero matrix element. And there's one small remark that I want to do here, is that this interaction, besides interaction between spin up, or spin down with spin down, it also allows the interaction between spin up and spin out and vice versa. So spin mixing is possible when the spin-orbit coupling is present. And here's what I want to demonstrate, the effect of the spin-orbit coupling on the band structure of the Kagome lattice. So the flat band of the Kagome lattice, highlighted by the red arrow, also gains dispersion when the spin-orbit coupling is present. Other degenerate C point inside the band structures, marked by this red circle, are also lifted when the spin-orbit coupling is present. And you can also see here, along some path in the muon zone near this gamma point, the spin-orbit coupling also split the degeneracy between spin up and spin down bands. And you can also quickly check that the spin-orbit coupling in this form does not commute with SZ, the Z component of the polyvectors. So when the SOC is present, SZ is not a conserved quantity anymore. And to demonstrate this, I calculate the expectation value of SZ in the following scenario. First, I only have the Zeeman term in the Hamiltonian, and this term means that I effectively put a magnetic field in the system. And this term uniformly add energy to the spin down band and subtract energy from the spin up band, and clearly separate them from each other. And SC in this case is either 1 or -1, so perfectly spin up or perfectly spin down. But if I add the spin-orbit coupling into this calculation, you can see just from the color that the spin, SC, can now take value between 1 and -1, and in some region you even see that the color turns to green, which means SC is almost equal to 0, and which means the spin is turning into the two-dimensional plane. And here, lastly, is the calculation with only the spin-orbit coupling, and you can see that spin mixing effect is still very dominant over here, and it also split the band of spin up and spin down here along the pathway near gamma. And here are some more band structure of the other lattices, and we know this by using the graphene parameter, and graphene is a conducting material. Most of our lattices, beside the gap between S band block and P band block, there are no other fundamental gaps throughout the muon zone inside the P block. So for example, this is the case for the snap square lattice. The band structure doesn't have any fundamental gap inside this block. Only two lattices the truncated trihexagonal lattice and the truncated hexagonal has fundamental band gap throughout the Bion zone inside the P block. And you can also see for these two lattices, they still have fully flat band over the whole Bion zone, even when the next nearest neighbor hopping and the SOC are present. And now I want to talk about the topological edge states. To calculate the Z2 invariant Nui, we use the full Kane formula. This formula is fairly easy to implement, but it only applies to systems with inversion symmetry. But lucky for us, most of the Archimedean lattices have this property. So what we do is, we go to all of the high symmetry points, or the so-called time reversal invariant momenta inside the Bion zone, calculate the eigenvalue of the wave function of the occupied bands at this point, and then multiply all of them together. So every eigenstate in this, the eigenvalue of the parity operator. So the eigenvalue is either 1 or -1. So when you multiply all of them together, the product is also either 1 or -1. So this is what we do. We occupy the band inside the bulk band structure and then calculate this product. And we see at which occupation we have a -1, because if Nui is even, then the product is 1, which means we have a normal insulator phase at that occupation level. But if the product turns to -1, we might have a topological insulator phase at that occupation. So this is the case that I want to demonstrate for the truncated trihexagonal lattice. The red band signifies the occupation level at which the product turns to -1. And then I look into the same energy window in the written band structure and try to find a band gap and see that there are two edge states bridging the band gap here. Another criterion that we want to check is the spin-orbit coupling, because we say that the spin-orbit coupling is the mechanism that allows this kind of topological insulator. So we check to see whether these edge states are there when the spin-orbit coupling is present, and they should not be there when the spin-orbit coupling is turned off. And this is the case also for this ribbon or for this lattice. When we also say that these edge states should act as spin current channel, so they should have high spin polarization. And I want to check that by calculating the expectation value of SZ, and I saw that these two edge states also have high spin polarization. And here for these two chosen points, the SZ here is almost equal to 0.9, and for the spin down band over here to this point, the SZ is equal to -0.85. And from the type binding calculation, you can also directly calculate the spatial distribution of the wave function. And I calculated that and used the spatial distribution as scaling to visualize these edge states. And you can see they are really indeed edge states because they are perfectly localized to the edge of the ribbon. And we also found for the same lattice but with a different edge configuration, the M-chain configuration, topological edge states, they are bridging the band gap, they are there when the SOC is present, not there when the SOC is turned off, and they have high spin polarization and localized to the edge of the ribbon. We also found the topological edge states for the truncated hexagonal lattice in the zigzag ribbon configuration, but at a much higher energy and a much higher strength of spin-orbit coupling. And finally, I want to talk about the quantum spin Hall conductivity. You can calculate the conductivity as a function of the Fermi energy or the occupation by performing this monstrous interval. I don't want to go into the details of this calculation, but I just want to make a few small remarks to this interval. So in contrast to the normal Berry curvature, you swap the velocity operator in the first term with this anti-commutator of the velocity operator in x direction with SZ. And one important feature is that in the denominator you have the square of the energy difference. So the conductivity should be large when the energy difference in the band structure is small. And this is the behavior that we've seen across the calculation that we have over here. And for real-world application, you can shift the Fermi level by applying a gate voltage or by doping. So in order to have good conductivity for the system, you should look for systems that have a peaks near the Fermi energy in which you can shift the Fermi level into, so you can obtain large conductivity. And now I'm at the end of my talk. So in conclusion, we can say that Archimedean lattices are promising flat platform to give rise to topological insulator. Although at this stage we are only able to found two systems that have this topological edge states, but at the moment we are only having the parameter from graphene, and we hope in the future when we can try out different Slater-Coster parameter from other materials that can form two-dimensional structures, then we can find these topological edge states on other lattices. And we can also see that these lattices still have fully flat band even when the spin-orbit coupling and the next nearest neighbor hopping are present. So they can give rise to strongly correlated system, because in the flat bands, the electron has no kinetic energy because the move velocity is 0. So the Coulomb interaction will dominate and will give rise to strongly correlated system. As outlook for future projects, I want to suggest studying non-dispersion on these lattices, because the Archimedean lattices have a lot of these small triangles group, which will give rise to a phenomenon called frustrated magnetism. So it could be really interesting to study spin Hamiltonians such as Heisenberg model on this system, and the orbital Hall effect, which is one new kind of orbital Hall effect that the group here study. And I will also continue working on this effect in the future on these lattices. And the last step, which I think could make a huge project, is to really realize these two-dimensional lattices with real materials, with atom or molecules. But for that, you will need to perform DFT calculation to check for stability. And I know that currently the group of Thomas Heider in Dresden are approaching this problem by trying out organic molecule. And now, I am at the end of my talk, and I thank you a lot for your attention. And special thanks to my supervisor, Dr. Nikki Trump-Hinscher, and Professor Ingrid Navish.